Okay, good afternoon, everyone. Can you guys see the screen?
Yes. Yeah.
Okay, great. Thank you. For today's lecture, we'll talk some interesting and latest topics in AI or machine learning. So specifically, we'll talk about foundation AI model and machine learning model transparency and some the hardest like generative model, etc. And at the end, we'll also briefly give you some of the guidelines or instructions how you can present the paper. So because the next lecture, we're starting to do the paper presentation, okay? Okay, so you probably heard of some of the words called foundation models, right? So basically, these models are trained on a very large volume data, right? So basically you can using data maybe curated from the internet, right? Images and text. So you can train this kind of a large amount of data, and this model is able to learn very generalizable knowledge so that the model can be adapted to a wide range of downstream tasks. For example, if you're doing the language understanding, right? So you can train this model like GPT-3, and you can using that to do a lot of downstream tasks like translation, prediction, and captioning, etc. And for vision, you can do the same, right? So you can train a foundation vision model, then you can take that model and fine tune for the specific application. So in general, we call these models foundation models. Okay, so this definition is actually taken from this paper, right? So these are the researchers from Stanford University. So highly recommend you read this paper, get an overview about the foundation models and some of the issues or problems or research challenges for this particular area. Okay. So before we look into more foundation models, first I want to ask, right, why are foundation models important, right? So why should we care about foundation models? Any ideas, thoughts? Yeah, just any thoughts you think of, that is fine. Anyone?
I have an idea. Maybe since they're trained on so much data and have so many parameters, they can learn a general representation, and that can be applied to other tasks.
Yeah. So I think your idea is that because we have so many different tasks, right, and we don't want to kind of if a different task, then we have to retrain the model. For example, you're doing object detection, segmentation, right? So although they seem like two different tasks, but the underlying, the learned representation should be very close to each other, right? Because you are basically trying to understand the object in the image, right? The semantic information in the image, right? So it'll be easier that if we have a large foundation model that is learned from a large chunk of data, right, from the internet. So this model knows well about the general knowledge. Then we can take that knowledge and easily do to some fine tuning or adjustment for the specific application or downstream task. Rather, if you switch to a different application, then you have to gather the training data, train the model, right, and do the testing on the application. So that's basically the purpose of foundation model. It'll be nice, right? Eventually, in all the AI applications, we only have one model, right? Whatever we do, we just go to this one foundation model, right? The knowledge is very generalizable, and the knowledge was learned from different different types of data, right? Not necessarily limited to text, image, right? We can learn from multi-modalities, right? So the knowledge are well generalizable, and we can easily use that for a specific application. Okay, so yeah, basically, if we have this kind of foundation model, right, it will give us a very powerful starting point so that we can develop AI system for the specific application or fit the specific needs, right? And these foundation models can support, development of advanced applications like chatbot, visual assistant, image recognition system, and maybe more complex autonomous vehicles. Okay. So here is give you like a figure shows the basic idea, right? How we can train this foundation model, right? So the data is the key, right? So we have a lot of data that can be collected from different resources, right? So we have text, image, speech, structured data, 3D signal, and more, right? So basically, it's like a human, right? We are not only learn from a single modality of data, right? We learn from the world, right? So whatever the data or the information signals we get, we process that into the knowledge for our future action, right? So here the idea is the same, right? We take different types of data, multimodal data, and we using these to train a model. And hopefully the knowledge learned, the representation learned by these large input data is able to adapt to different tasks, right? Here we have a variety of tasks, right? Question answering, sentiment analysis, image captioning, object recognition, and maybe you have to also have some tasks like video understanding, right? So you have a very different task, but we are able to leverage the knowledge from this foundation model and easily adapt to the specific task. So there's many foundation models. Here we want to take a example. We're using CLIP model as an example to give you some of the idea, right? How this model is being trained and what kind of applications we can use these foundation model. So CLIP is stand for contrastive language image pre-training. Okay, so based on the name, you can see that, right? So this is a pre-training. So this is a model using some of the technique for in the pre-training stage, right? And the data they're using is the language data and also image data, right? So basically you can take the text and image and to train this model, okay? So once the model is trained, it can be applied to natural language processing and a computer vision task, right? Because the model learns the representation from text, from both image and text, okay? And it has been widely used in all AI applications, right? Here, later, after we introduce the CLIP model, we'll see a couple of applications, right? So how, CLIPs has been applied to some of different applications. Some of them are very interesting. So for the CLIP, right? So here, as we mentioned, it take the text and also image as input, right? So to train this model, the authors actually collect a large set, right? So have 400 millions of image text pairs, mostly from the web. Okay, so those image and text pairs, you can get is from some of the internet or some of the website. For example, the Facebook, right? Instagram, right? So people YouTube. People usually, upload an image, you will have some hashtag, right? So this is the photo of dog, right? Look at my cute dog, etc. Right? So in this case, you inherently has a pair, right? So the image and the corresponding text. Some of them may not be very accurate, or some of the information may noisy, right? Because the user may not only describe this object, but also describe some other information, right? And maybe the grass, or maybe talk about the weather or something like that, right? But there is some noise into the data, but still, by collecting a large of such data, right? So the main information are there, okay? So we have this kind of pairwise input data, right? An image has the corresponding text description. Okay. So once we have construct this training data, right? So because we have two different data input, one is the text, the other is image. So the method using two encoders, right? One is for encoding the feature for the text. Okay, so this is can be they are using the vision transformer. Okay, I mean using the transformer architecture, right? So because that's the most powerful architecture to do this kind of sequence modeling. Okay, so you have a transformer architecture to encode the feature from the text. Also, you have a transformer architecture, right? Vision transformer to represent the features from the image. Okay, so let's consider if there's in a batch, right? When you do the batch processing in a batch, you have n different n pairs, right? Text and image. So you generate these for the image, you generate this feature embedding I1 to IN, right? Similarly, for the corresponding text, you also have this text embedding, right? T1 to Tn, right? So indicated by a different color, this purple one, okay? And then we can actually measure the computer correlation or measure the similarity, right? And because we have this sort of pairwise fashion of the data, right? We know this image accompanied with this image is this particular text. So this is kind of like a positive pair, right? So in this case, you can construct these kind of similarity matrix, right? And on the diagonal, right? So the diagonal element, so this is supposed to be the positive pair, right? So their correlation should be the highest, right? Because they corresponding to the same semantic class, right? For this particular, if you look at this one, right? This is the class of a dog, right? The text and image should all have the semantic meaning, right? Describing this particular dog, okay? But for the other, like off the diagonal, right? Because these are, if you look at I1, right? The T2, T3 are the description from other image, right? So you want their distance to be far away, right? So this is we learned this from the contrastive learning, right? So for the positive pair, in the feature embedding space, we want them to be close to each other. But for the negative pair, right, we want them to be far away from each other. Okay, so they're using this kind of contrast learning to train this pairwise data. Okay, so once the data trained, the advantage of this CLIP model is it can be used to do zero-shot prediction. Okay, so zero-shot prediction means this image or label has not been seen in the training, but this model is able to predict unseen class. Okay, so basically you can feed this kind of text prompt, right? So a photo of something, right? This is basically ask the model to fill the blank, right? So in this parenthesis is a class, right? You want the model to predict, right? A photo of dog, a photo of a cat, right? So here, basically, you using this CLIP model to do the text embedding, and you also have this input image. You get this image feature embedding, right? Then you basically for all these classes and which one give you the highest probability, right? The highest correlation, similarity. Then you using that as a prediction, right? So for this particular example, this input is a dog image, right? So here, the dog here will give the highest correlation or similarity. Then we can using that as the prediction, okay? So here are some notes is that for this, there is also research on this kind of prompt engineering, right? By changing these kind of input, right? Not just a photo of, you can say an image of something, right? Or maybe a natural image, right? You can make up this kind of text prompt. This may give a different or some different result overall, right? If you have a set of data set, the accuracy may vary. So there is actually some research on how we can engineering, right? Do some prompt engineering, or we can come up with some learnable prompt so that the prediction can be maximized. Okay. So let's look at a couple of examples, right? How once this model is trained, how accurate it is able to predict, the object, right? If we're doing image classification or object recognition, right? So here the author tests a set of different data set. So one is this food 101. So basically this data set contain different types of food, right? So in this example, this is the guacamole, right? So you can see that a photo of a blank, right? So ask the model to predict. And the model is actually able to predict the right class and also give some of the explanation, right? This is a type of food, okay? So this is, as I mentioned, right, this is one type of, doing this kind of prompt, but you can definitely change another different prompt to ask the model to generate some prediction. And this is another example. They do this on this Sound 397 data set. And this is the model predict. This is a television studio, right, which is out of these 397 labels, right, this television ranked the first, right? So actually has a very high probability. Okay. Anthony, do you have a question?
Yes. So I was wondering, in the case of this clip network, the text and the images have some sort of relationship, right? Because that's the point of the task.
Right.
So in foundation models in general, do all the types of data need to be connected in some way to contribute to the task? Or is this just one example of a foundation model?
Yeah, in general, it should be something similar, right? Otherwise,
Okay.
you're basically just feeding garbage, right? You confuse the
Right.
model,
Okay.
right? If there's those information are totally unrelated, then the model wouldn't learn anything meaningful, right? Yeah.
Okay. Makes sense.
Yeah. Okay. Okay, here's another example, right? So these two are natural images, right? They are able to do very good in terms of making the accurate prediction. So the author also look at other type of data, right? These satellite image, right? Basically have a totally different view, right? So this is like the top-down view, right, from the satellite imagery, and also the content can be very different than the natural image, right? So these are some of the grass field, right, crop field, right, and the model is also able to predict, right? This is the crop land, right? Actually has a very high accuracy, right? Ranked 4 out of the 10 labels. And some other, the top 3, right? Also very similar, right? Highway, maybe this is not very accurate, right? It's not a highway. Maybe they treat this like a highway or roads. But for someone like the land, right? They are able to recognize this is a type of land. Okay. And also for the medical image, right? So it's also able to do a very good job doing these kind of classification for medical images. And also for video, right? So we can not only do image classification, but we can also do video classification, right? Because we can treat the frames of the videos, right, as an image. Then we can do this kind of frame by frame prediction, right? Feeding the model each of the frame and ask the model to make a prediction, right? A photo of something, right? So then maybe if we take a couple of frames, then we can do like a majority voting, right? So to come up with the label for the entire video, right? So for this one, the model is able to predict, right? This is the country line dancing. Okay. Okay, here's another showcase some of the applications for clips, right? So if you have a database, right, maybe you have a personal album, maybe you travel a lot, right? So you have a lot of photos taken from different places you've been traveled to, and maybe you want to, create some like a memory book or album, right? Maybe you want to search a particular photo, then you can put into some of the keywords, right? So for this example, right, they have a database and they want to do this kind of search based on the text input, right? Animals in the long grass, and these are the retrieved image, right? Can kind of fit this text description, okay? I can think of, based on this, another applications we can do like in the surveillance or video scenario, right? We can do text retrieval as well, right? Maybe the police is interested to find us, suspect vehicle, right? Looking for a white collar truck, right? A particular type. Then if they have a, video surveillance database, then this CLIP model is able to retrieve all these maybe frames, fits the description, right? Then maybe we don't have to go through all the videos frame by frame, trying to identify those useful information, right? This machine learning model is able to automatically do like a first round of screening, right? To get the useful information we want, right? So that's another maybe potential application I can think of based on this image search, text-based image search. Okay. And this is our recent work. We are doing this problem behavior recognition in videos, right, for children with autistic spectrum disorder. Okay. So basically we want to recognize these problem behaviors for children with autism, right? These are flapping, head banging, spinning. And, we can do, the typical way is we can come up with the video action recognition algorithm, right? To treat it as the normal action recognition, right? To train the model and recognize the action in the video. And we found out that, some of the actions, especially these are the young kids, right? Even, babies, right? Less than 1 year old. Some of the actions are very subtle. They don't have a lot of distinctions based on purely the visual appearance. So the idea we have is, can we, leverage some of the pre-trained, language vision model, right? Like the CLIP, to help or assist the training, right? To bring additional supervision to learn a better representation from the video, right? So the idea is that we can easily get the description of these different actions, right? Arm flapping, this is something we actually search for from Wikipedia, right? So they have some definition, right? What is arm flapping for this kind of people with ASD, right? So this basically a type of stimming action behavior. So you can also try to find some formal definition from some articles, right? Maybe from a domain expert like a behavior analyst, right? So we can generate these kind of description for different types of actions. And then what we can do is we can, using these easily generate text for each type of action, right? We can using the CLIP, because CLIP has the text encoder and the vision encoder, right? We can leverage these pre-trained CLIP text encoder to generate the feature embedding for this input action, right? If this is a spinning and this is the corresponding, action of the video, right? With the contain the action of spinning, and we can make sure that the visual embedding should be very similar or align well with the text embedding, right? Because they corresponding to the semantic class, right? So actually, we are using this pre-trained CLIP model to provide some of the assistance during the training, and of course during the inference, right? Because we don't know the label of a new test video, right? We'll just rely on the vision branch. But during the training, right, for each of the input video, we know the ground truth action label, and we can generate the rich description for the action label to generate this kind of text embedding to assist the training, to help hopefully make the vision representation better, right? Some of the description of the spinning, right, may force the network, the vision network, to focus on specific region, right? The spinning or head banging, right? The description specifically mentioned the head maybe, hitting on some of the stuff, right? So this will force the network pay attention to maybe the head region in this video, right? The representation can be learned better to distinguish head banging from other action classes, right? For some actions, they involve hand movement, right? Like arm flapping, etc. And because, we can consider this is like a free launch, right? Because we are not doing any annotation. We basically take the action, right? We can using GPT-3 to generate some text, or maybe you can search on the internet to find the description. Then we can using the CLIP model to generate this kind of feature embedding to help or to assist the training of the vision model. Okay. And based on the result, right? So this, video swing transformer, right? So VST stands for video swing transformer. So this is only the video only, right? We only rely on the video to train the model. This is the recognition accuracy, 90.94. But if we consider language during the training, to assist the training, we are able to boost the performance by around 3.5%, right? So this is, consider improvement, right? Given that we are using some of the freely available text description and off-the-shelf CLIP model to help improving the training or the learning of the vision branch. Okay. And this is another example. They using the CLIP model to do the animal pose estimation. Okay. So the pose means basically the key point or key joint, right? So they are targeting animal pose estimation, but in general, we can also apply to human pose estimation, right? Human pose estimation is a very important task for gaming, movie, those production, etc., right? So the basic idea or the output should be predicting these key point of joints of animals or humans accurately. Okay, so they trying to also using the CLIP to help understand some of the semantic better, right? So basically the key point are no, right? So let's say we have maybe 10 or 12 key point, right? The nose, right eye, right knee, right? So these are the description of the key point. And, we can take this text input, right, prompt, and go to this CLIP text encoder to generate some of the feature embedding, right, for these text. Again, this is easily, available, right? You don't require additional annotation effort, right, because these are like predefined. And you can also take the image and go through this kind of visual encoder to generate the features, and hopefully you can using this kind of feature aware adaptation or alignment, right? For each particular joint, the learned visual representation should be aligned with the text description, right? This is the right knee or this is the left knee, right? So with this kind of idea, they are able to do this kind of spatial aware adaptation, understand, right, the spatial position of different joints, so that the estimation can be more accurate. Okay. So this is another application of using the CLIP. So there's a lot of things you can think of. So I'm not going to give you more examples, but definitely, if you, for some applications, you feel like, okay, you can bring some of the knowledge from the text description, then you can, resort to CLIP or other, language vision pre-trained model. Okay. And for the medical world, right, so there's people also using CLIP to do similar things, right? So here for this MedClip, if you have a set of database, right, with different applications, right, maybe doing this kind of tumor detection, right, different some of the radiology analysis, right? So you have these ultrasound, CT or different type of data, right? So you can using the clip or train a clip on the medical data, right? So that you have a medical clip version rather just the natural image version, so that for your application, then you can input some of the text, right? Like a CT image contain long, right, or maybe some other type of text query you have, and you are able to retrieve the corresponding or relevant images. Okay. And this paper using the clip to do the visual question answering, right? So this is getting very popular in the medical domain, right? So basically kind of generate a very rich text description, right? You can have a question query, right? So here, like CT of the chest, right? And there's like thick wall cavities in both up lobes with diffuse tree in bud nodularity, right? So basically some descriptions of some of the, for this particular input medical scan. And you can train, if you have this kind of pair of data, right? The description and the image, then you can train using the clip, right? To train this kind of model. And then you can using this trained model to generate descriptions, right, for a new input, right? So the query will be the question, right? Some of the medical questions, and the output will be the corresponding answer, right? So maybe a description fits the question. Okay. And here's some of the example, right? So the question is, where's the lesion located, right? So this is the I think X-ray image of the lung, right? So this model is able to give out some of the answer, right? So this PubMed clip is their approach, and the right answer is the right lower lateral lung field, right? So they are able to correctly predict this kind of answer. Okay.